notes section, I want to talk about Lewis structures with ionic and covalent compounds. And this is a very important basic skill that AP likes to test students on. So this is the section that you probably want to make sure that you're pretty familiar with it so that you can draw dot diagrams or Lewis structures for either type of compound. Okay, so this situation, we're talking about covalent compounds. Please remember when you do talk about ionic compounds, they tend to transfer their electrons. So if you were to draw a Lewis structure of an ionic compound, you would have the cation have no valence electrons around it. And then for the nonmetal, you would have 8 valence electrons around it. When you're talking about polyatomic ions, that is a covalent structure that happens to have extra electrons. So it may have a positive charge, it may have a negative charge, and we'll talk more about that. Okay, so here's an example of a compound that is covalent. Notice that they're both nonmetal, and they're showing that each atom has a certain number of valence electrons. Now notice phosphorus has 5, so anything in that family tends to have 5 valence electrons. And chlorine obviously is with the halogen family and it has 7. But because of its subscript, you have to multiply that by 3 to give you a total of 26. So you have to be really good at recognizing the number of valence electrons and then applying the subscripts for those atoms. Now, when I'm teaching students how to draw Lewis structures, I typically look for the atom that has the least number of valence electrons because that's the atom that tends to want to share its electrons the most. You could also use the idea that the atom that has the lower electronegativity is the one that's going to be in the central atom because it's very good at sharing its electrons. Now, please, please, please do not put something like hydrogen in the middle of a Lewis structure. It only has the capacity to hold 2 electrons, so it will never be in the middle. It'll always be on the outside. The exception would be if hydrogen is bonded to itself. So obviously it would almost be considered a central atom. But most of the time it is always on the periphery or the exterior of a Lewis structure. Obviously helium is another element that only has room for 2, and it typically does not want to bond with another atom. So it typically has a full octet, or a full shell, I should say. Okay, so here's an example where they put phosphorus in the middle and chlorine on the outside, and notice that every atom should have 8 electrons around it. However, if you look at phosphorus, it really only has 6. So you're not done. You need to add a second set of electrons, or I should say 1 pair of electrons over phosphorus. Eventually we're going to talk about what kind of shape does this molecule have, because you'll notice that lone pairs, they tend to change the shape of the overall molecule. So notice that in this situation they added up all the electrons that they had for that molecule and they were left over with 2, so as a result of it they had to put 2 on top of phosphorus to finish off the molecular structure. So please remember that you want to fill the octet for the surrounding atoms, and then if there's anything left over it goes into the central atom. Okay, so here we have an example where we have carbon, which has 4 valence electrons, and oxygen, which has 6, but we have to double the number of electrons for oxygen since there's a subscript of 2, and together they equal 16. Now, what I would do is I would look at which one is the least electronegative, or the one that has the lower number of valence electrons, and notice that carbon does. So as a result of it, carbon goes in the middle, and you can put 2 covalent bonds between carbon and oxygen, but then you have to start thinking about how many more electrons do you have left. So notice that in this situation they've completed the octet for oxygen, but carbon only has 4. So as a result of it, we have to start thinking about multiple bonds. So when you look at the molecule, we used up all the electrons, but we need to figure out how do we complete the octet for carbon. So typically what happens is we have to move electrons around and create multiple bonds. As a result of it, we give carbon its set of 8 electrons, and we also give oxygen its set of electrons. So we are able to satisfy the octet for both sets of atoms. Okay, here's an example where we might have to do a triple bond. So notice that hydrogen is on the periphery. It only needs 2 electrons, and it's perfectly fine with that. But carbon and nitrogen both want to have a full octet, and as a result of it, they have to share more electrons in order to get that full octet. And once again, carbon is in the middle. It only has 4 valence electrons, and you could argue that it's lower in electronegativity than nitrogen, so as a result of it, it is a central atom. Okay, here is a polyatomic ion. I would make sure that you know how to draw polyatomic ion Lewis structures. And the important piece is that it has an overall negative charge. And when we talk about formal charges in a little bit, you'll see why it has an overall negative charge. So notice something different is going on here. You could argue that iodine's doing something very interesting here. Notice that it's lower in electronegativity. Oxygen has 6 valence electrons. Iodine has 7. So they chose to put iodine in the middle because it's lower in electronegativity. So even though it has more valence electrons, you could argue that it's a better central atom because it's lower in electronegativity. So as a result of it, oxygen is on the periphery, and as a result of it, they had to count up a lot more electrons here. So notice iodine has 7, oxygen has 6, but there's 3 of them. So they had to multiply it by 3. Plus, if you have a negative charge, you have to add an electron. And as a result of it, this works out to be 26 electrons. So notice that iodine has its octet filled and oxygen has its octet filled. And you're probably wondering, where do you get that -1 charge? Well, we kind of have to look at formal charges to get that overall minus charge, and we'll talk about that in another lecture. Okay, here are some exceptions to the octet rule. So you need to know that there are certain atoms that are okay with not having 8 electrons. Now, boron, notice that boron has the ability to have less electrons. So boron is one of those exceptions to the rule where, because of its core charge, it is okay with only having 6 electrons within its octet. Okay. And once again, they put boron in the middle because it's lower in electronegativity. You could argue that it also has less valence electrons, and as a result of it, it's the central atom. But notice that fluorine is highly electronegative. It does want to complete its octet, so that is why it's in the periphery. Okay, now you could have the opposite problem where you have lots of extra electrons. And the amazing thing is, if you look at rows 3 through 7, so periods 3 through 7, you will find atoms that actually are able to succeed or overcome their octets. And the reason why is they have access to d orbitals. So even though we don't see d electrons in the p region of the periodic table, you could have something like phosphorus or sulfur where it has access to its d orbitals. Now, we typically look at d orbitals when we're looking at transition metals, but because those atoms have the third energy level, they do have access to their d electrons, or d orbitals, I should say. So here's an example of an expanded octet. So notice phosphorus, um, it is lower in electronegativity. You could argue it also has lower valence electrons. They put it as a central atom. Now you would say, well, wait, why can't I make chlorine the central atom? But please remember that chlorine is actually more electronegative, and it's not as good at sharing electrons, whereas phosphorus is much better at sharing electrons. So that's why it's going to be a central atom. And as a result of it, phosphorus, because it's in the third energy level, has access to d orbitals. So it could actually accept more electrons than most atoms. So as a result, it has 10 electrons as a central atom. Okay, here we have sulfur, and sulfur, once again, is one of those atoms that it's in the third energy level. It has access to d orbitals, so as a result of it, it is okay with having expanded octet. Xenon, okay, xenon, which is atomic number 54. Now you might say, well, wait, that's a noble gas. Yes, well, we see some interesting things happening with krypton and xenon. They actually are okay with having covalent bonding. Um, so, granted, we're talking about the fifth energy level. Um, Xenon is able to expand its octets using d orbitals. Okay, so we will eventually talk about formal charge so that way we can figure out why a polyatomic ion has an overall negative or positive charge.